Good afternoon, everyone. We are live.
Hey, everyone. Welcome to the 17th episode of the Stanford MLSys seminar series. I'm Karan. We have with us today Dan, Piero, Fyodor, and Matej as well as joining us today, and our guest, Savin Goyal from Netflix. Today, we're going to be chatting with Savin about the data science that happens at Netflix, especially around the ML modeling workflow. So as always, there will be a talk for 30 minutes and then a 30-minute podcast style discussion where you can ask questions and we'll relay those to Savin. Let me talk a little bit about Savin. He's a software engineer at Netflix who's responsible for Metaflow, which is a ML platform that Netflix, and he focuses on building like generalizable infrastructure to speed up data science at Netflix and beyond. And he's going to be talking about taming the long tail of industrial ML applications today. So we're very excited to have you in, Savin, and take it away. If you can just try to share screen.
Thanks, Karan.
Awesome. Yeah, looks good.
All right. All good?
Yes, looks great.
Okay. Thanks for having me, Karan. So today I'm going to talk about how Netflix thinks about building machine learning applications. And for folks in the audience, you know, when you think about Netflix and machine learning, the very first thing that pops up are our recommendation systems. But in reality, they sort of like happen to be the tip of the iceberg. And we have made huge investments in other machine learning applications over the years. Let's take a look at what those look like. So at a really high level, if you look at Netflix's business model, right? Netflix is involved in licensing content, producing its own content, and then we make that available through a bunch of applications, a UI on the TV, an application on the web, applications for your cell phones, Xbox, PlayStations, you name it, all in the hopes that we can delight our users. And users, when they're happy, they'll pay us more and more money, which we can then again pump into getting more content on our service and marketing it more broadly. So that then again, we can collect more users. And as this sort of like flywheel kicks in, that sort of like guarantees that as a business, Netflix succeeds and thrives. Now, as we sort of like start scaling for each of these different components, we need to become more and more intelligent to eke out the last mile optimum usage. So think about it in this manner, right? Like the more content that we have, the more intelligent we need to be in terms of presenting the right content to the right audience at the right time, which is more around solving the discovery part of the problem that many people are familiar with, the recommendation problem that Netflix tries to solve. Then once the user actually ends up clicking on a content that they are interested in watching, then we need to be rather intelligent in terms of how to effectively stream that content from our data centers to the user. And for that, we have built up our own content distribution network. So every few hours, we need to predict what kind of content is going to be popular in your neighborhood so that we can seed those hardware boxes with that appropriate content so that you never run into rebuffers. We also need to be super intelligent in terms of how do we effectively encode our audio and video assets so that we are not clogging your internet bandwidth. Now, as we sort of like delight our users are giving us more money, and we need to make sure that we are making effective use of that money in terms of divvying up for marketing our content to more and more newer users in newer countries that we operate in, as well as investing in content. So we need to identify what kind of content keeps our users engaged. How do we sort of like accurately value the content in monetary terms? And then as we are sort of like becoming a big studio by itself, you can imagine, you know, creating content is a very human-intensive endeavor, figuring out what scene should be shot where, on what day, who gets to be part of our shows, when do we need to release a show on our service, how do we do automated quality control, how do we manage budgets for the show. All of that, again, is at the end of the day an optimization problem. And solving for that requires a variety of different machine learning techniques. So Netflix, over the past very many years, we have assembled, you know, hundreds of data scientists internally who are working on all of these different problems. And the scale of these problems, they vary from, you know, all the way from, hey, we have like a huge content distribution network. How do we figure out which content is going to be popular in which geography in real time, to, hey, we need to submit a video encoding job into our compute cluster. And I just want to know how much time it's going to take for that job to finish so that I can just like step out and grab a cup of coffee. And all of these different problems, they essentially form what I call the long tail of machine learning applications. Each of these problems by themselves are really, really important for the business to sort of like make forward progress. But then at the same time, we need to make sure that our users, they are able to, our internal data scientists are able to provide value, are they being productive while they sort of like build these ML applications by themselves. And that's where my team comes in, trying to figure out what tooling can we provide to our users so that they can be much more effective in their job. Now, let's look at a data scientist, who is, say, employed at Netflix or any of these other companies, because most companies, when it comes to business data science, they have very similar problems. The role of a data scientist is ultimately at the end of the day to optimize a business metric. And the way they go about doing that is first, they'll spin up some sort of an IDE. If you're a Pythonista, then maybe you're using a Jupyter notebook. If you're more in the R landscape, then you have an RStudio IDE. Maybe you're using Vim, Emacs, PyCharm. Usually there's some IDE that you would prefer. And now the beauty of the open source landscape is that there are incredible innovations that are being made in terms of just like pure machine learning libraries, right? If you look at the communities behind TensorFlow, PyTorch, Hugging Face, OpenCV, there's a lot of work that's now rapidly available to larger as well as smaller organizations from the open source community. So our data scientists, they can very easily spin up their notebook, they can do a pip install TensorFlow, and then they can get tracking on the data sets that they have. Now, in the industrial landscape, in organizations, things sort of like become slightly interesting. Okay, so now you have to essentially, deal with data. Ultimately, at the end of the day, if you're training a model, if you're playing around with data, you need to access that data in some form. Many times that data is available to you as part of your local disk, maybe some CSV files lying around in your local folder. Many times, maybe you're talking to a cloud service provider. Maybe your data is stored in S3 or Google Cloud Storage. It's not just the data that you need to keep track of. As you sort of like go about doing your work, you need to also keep track of your work. You need to keep track of all the metadata that you are generating. And there are open source solutions like MLflow that you can use to sort of like write the progress that you're making back to some of the disk-based storage. Now, all of the work that you're doing so far, which is around like, okay, I have my data, I've done my analysis, now I'm able to train these models locally on my laptop. Ultimately, at the end of the day, you need to sort of like create a workflow out of your work. It could very well be the case that your local compute instance, your laptop doesn't have the necessary resources to train your models. So maybe you want to offload some of that compute onto the cloud, onto say a Kubernetes cluster. Maybe you want to run a hyperparameter optimization. So maybe you are integrating with SIGOpt and you want to offload that compute somewhere. Maybe you have a high performance computing cluster hidden somewhere in your closet and you're interacting with that through some workload manager. But now slowly and suddenly, the data scientist is stepping away from data science work and sort of like entering more into the engineering realm. And they have to sort of like get themselves familiarized with all of these concepts, like, okay, like what are the Kubernetes APIs and how do I sort of like orchestrate my jobs on, say, a container orchestration system and so on and so forth. At the same time, another thing to sort of like keep note is that many of these machine learning workflows, they sort of like don't exist in isolation. Usually the input to these workflows is changing all the time. Maybe you're reading some table that's being written to Amazon S3, and every single day or every single hour, you have newer data that's sort of like showing up in those buckets. So now you would want to make sure that your workflow can read either the latest or the last few copies, and it can retrain itself ever so often. And to do that, people usually, once they are happy with the workflow, once they're happy with their work, they usually export that work on top of a workflow orchestrator. And in the community, there are many different options. Airflow happens to be super popular. workflow orchestrator that came out of Airbnb. Then there's Argo, which will essentially help you orchestrate your workflow on top of a Kubernetes cluster. There are managed offerings as well, like Step Functions by AWS, all of which essentially allows a user to essentially, at the end of the day, rewrite their workflow and then sort of allow it to execute asynchronously on top of some compute resources. But then from a data scientist point of view, they now need to learn yet another tool and sort of like rewrite a huge chunk of their work to fit into this new paradigm so that then their workflows can run asynchronously. Now, most of these workflow orchestrators, they essentially orchestrate Docker containers or containers of some sorts, right? So now our user, now the other thing that they need to sort of like figure out is, how do I take my units of compute and package those into containers? And now our user is expected to essentially write a Docker file, understand what different package managers are, so that, you know, if let's say they intend to use TensorFlow on top of a GPU, they are able to install the necessary drivers as well as the packages within that Docker container. Again, you know, like not impossible, but a lot more engineering work that our user is supposed to do. Now, once the model workflow pipeline, the training pipeline has been deployed, the model by itself has very little value. So you need to essentially integrate that model into the surrounding ecosystem, which means that, you know, you are essentially either writing a Flask app, or you're hosting a Shiny dashboard. Maybe you're writing a custom application that you're deploying on top of Kubernetes clusters. And now if these are web services, then you have to figure out a CI/CD story. Again, you need to keep in track like what your model drift is. There are like a whole bunch of commercial as well as open source solutions that allow you to sort of like monitor in real time how your services are performing. So you need to make sure that you're really at the top of your game in terms of knowing what each of these infrastructural components offer to you and how to sort of like make the best use of them. And then finally, you're able to sort of like power either an internal dashboard that your internal business stakeholders are looking at, or you're able to power the Netflix recommendation experience, or maybe, you know, you're just sort of like writing a memo at the end of the day based on some of the predictions that you have gathered. And now, once you sort of like, at the end of the day, point your users, point your business stakeholders to these dashboards, two things can happen. Your business stakeholders do not like the results, which means that much of the work that you did was wasted effort in some sense, which is okay. You know, ultimately in machine learning, you are trying to model the reality, and many times, many of the experiments just don't pan out. And at that point in time, the ones sort of like feeling that the data scientist would have is that, okay, was there a way where, you know, we could have gotten from this initial idea and gone through the ETL cycle, the Dockerization of the processes and everything else as quickly as possible, so that they could have gotten to this end result that, okay, you know, like the idea doesn't actually really hold much promise, as quickly as possible. The other thing that could have happened is that the business stakeholders, they really like the results and they want more models, more progress. And that will actually complicate things even further, because now the data scientists, now they have to iterate and prototype more ideas, maybe add more features, maybe now there'll be more people who will join the project. And how do you make sure that multiple people can collaborate? How do you make sure that you can run sort of like staging pipelines and deploy staging workflows and staging services without actually overstepping on anything that's been deployed in production? And at that point in time, in many organizations, and it definitely used to be a thing at Netflix as well, that other engineers would get looped in, or there would be sort of like a stop the world pause, where people will start to re-architect their workflows, their pipelines, their style of work, so that then things can become more shareable and more people can collaborate and effectively contribute to the project. But all of that at the end of the day impedes productivity. And so the goal of my team's existence at Netflix is, okay, can we sort of like identify what are these paper cuts, what are these tools, what are these issues that people run into every single day that allow them, that are not allowing them to be as productive as possible. One thing to sort of notice here is that if you look at most of the tools that I've sort of like laid out here, every single thing is either an open source tool or it's available as a managed offering by one of the public clouds. So independent of whether you are, say, a one-person startup or if you are a big company like Netflix, you would essentially have access to more or less the same kind of tooling. But still, there is something missing in this diagram, which does not still allow folks to be as productive as possible. So if we look at, say, this data science stack from another angle, so any organization which needs to invest in machine learning, they need to have some story around their data warehouse where all the data resides. Then they need to provide their end users, their data scientists, access to some compute resources, GPUs, CPUs, some way of orchestrating their jobs on top of those compute resources. So these could be some workflow orchestrators like Airflows of the world. Then our end users, our data scientists, they need to figure out how to effectively write against these schedulers so that they are able to prototype locally as well as in production, as well as all the model operation concerns around like reproducibility, repeatability, collaboration, model monitoring, all of that should be taken care of as well. And at the very top comes the real meat of the problem, where the end user actually gets to work with their favorite machine learning libraries, their data assets to figure out how to solve the business problem that they were originally tasked to solve. And from a data scientist's perspective, the opinions that they really care about are, what kind of IDE do I want to use, or what kind of machine learning techniques do I want to use? What package do I care about? But they wouldn't necessarily care as much about like, where are my GPUs coming from, as long as they have quick and easy access to the compute resources they want. The data scientists, they notionally care about how my data is being versioned, how my code is being versioned, so that I can go back in time and I can reproduce results. But the actual semantics of how it happens, the nitty-gritty details, if that's abstracted away, data scientists wouldn't care less. On the flip side, if you look at the infrastructure investments that an organization needs to make, like at the top level, you have amazing work being done by the community around like TensorFlow, PyTorch, all of the great machine learning ecosystems. So organizations by themselves don't necessarily need to invest a lot much more at the very top levels. But yes, they need to figure out how to set up a data warehouse, how to manage a Kubernetes cluster. If, say, we are deploying Airflow, how do we manage that? What are our best practices around model operations? And those are all very big infrastructure problems. And our goal with some of the tooling that we built internally at Netflix was, can we sort of like provide an opinionated library of sorts, which enforces stronger opinions on the lower levels of the stack, but allows our end users to completely determine how they want to actually go about doing their own work. So let me sort of like dive a little bit deeper and convey what it actually means in practice. So the programming model that Metaflow, our machine learning framework, essentially exposes is that of a DAG, which we believe is a very natural way to express machine learning pipelines, which is essentially what workflow schedulers also do at the end of the day. And in this example, you could have a start step where you are reading some data from a data warehouse. Maybe you are doing some feature processing on top of that. And then say you're training two different models, model A, model B. And then in the joint step, you might be just interested in understanding which model performs the best. And then in the end step, you might be just storing that model somewhere or integrating it with the surrounding ecosystem. And there could be multiple other variants of this DAG as well. So when we allow our user to essentially expose their compute as this DAG, so the way it essentially happens, let's take a look at this example, right? So very simple, straightforward example. We have this function fit model. What's really happening in this function is the user is executing a Spark SQL job, getting some input data as a pandas data frame. They're transforming that pandas data frame into features, and then they're training a random forest model. And then they're dumping that model, say, as a pickle file somewhere. Now, with Metaflow, they can very easily refactor their code into a workflow. So Metaflow introduces notionally these two concepts of a flow and a step. So you can have a training workflow, and now you can essentially just annotate some functions with this decorator step. And in this example, we have the step build features, which is essentially launching a Spark SQL job, and then it's transforming the input data into features. And then with the self.next function call, we are essentially determining what is the next step in the workflow. And the next step happens to be fit model, where we just very easily import scikit-learn, we train a model, and then we just assign the estimator to self.model. So it seems pretty simple, standard, straightforward, no magic over here. Now, with Metaflow, what you can do is just like, your previous example of the fit model script, you could have very easily just executed that with like Python fit model.py. You can very easily, in a similar way, execute your workflow just by saying Python myflow.py run. And then the Metaflow executor will take care of executing these steps in order, a topological order for your workflow. Now, because we were able to specify the compute as a tag, now we can become pretty creative in terms of some of the functionality that we can introduce. So for example, in any step, anything that you store, so for example, in the build feature step, we are storing the self.feature, self.target. Notice that those values, because it's idiomatic Python, we are writing a Python class. So no magic over here. These values are available in when you call like estimator.fit, self.feature, self.target. And then in the next step, we are just storing the estimator as self.model. Now, what Metaflow will do behind the scenes is that it will actually store every single of the one of these objects in the backend data store, so that then at any point in the future, you can go out and you can retrieve and inspect that data set. So in this example, our user is spinning up a Jupyter notebook, and they are interested in the latest execution of my workflow. What was the model that was generated, and Metaflow will take care of assembling all of that information for you. And not only that, everything is versioned and namespaced by default. So if I go back, if you notice, this workflow has a run ID 724, and it will, when I execute this workflow, it will actually execute in my own namespace, so that I can actually go back and then I can say that, hey, I am only interested in looking at the data which is for my namespace, for say, like the latest run that I have, or any of the previous runs, and I can very easily tag this information. And that sort of like helps in experimentation management. So use cases over here could be that I'm iterating on multiple different versions of my model, and I can essentially make my code changes, execute my script, without actually having to worry about like, hey, did I git commit my code? Did I store all of my input parameters in a notebook or something of that sort? And I can go back in time and I can sort of like recreate all of my work history. The other sort of like interesting side effect of storing everything by default is that now I can actually go back in time and restart from any step. So let's say I have a workflow, that workflow failed at a particular step. Then I can go back to my code, I can fix up my code, and then I can just resume my work from a particular step, because all the previous history is already being snapshotted by Metaflow, so that you can replay that and make sure that the user is able to make forward progress. Now, another sort of like interesting use case that happens very often is that our users, they don't want to train a single model. In one shot, they want to train multiple models. And for that, we want to make sure that we are able to provide them very idiomatic interfaces. So in this example, our user is setting up a parameter grid, and now they want to essentially run this step fit ElasticNet against each of the entities that are part of the ElasticNet parameters. And they can do that by very simply saying that, hey, like my next step, which happens to be fit ElasticNet, it needs to execute on every single element of ElasticNet parameters. And Metaflow will then essentially take care of farming out those jobs and executing those. So let's say if our parameter grid had 3 different parameters, then Metaflow will take care of very easily running those steps in parallel so that our end users, they don't ever have to worry about how to write parallel code, and will take care of everything on behalf of the user. Now, the interesting thing that comes next is all of this is fine and good when our user is within the confines of a laptop. But very soon, and it's definitely the case here at Netflix, that many of the models that we train don't fit into the resources of a single laptop. Many of the data assets that we process, they can't fit into the resources that you get of any local workstation. And at that point in time, we allow our users to just simply annotate some of their steps with the kind of resources that they would need for many of these functions, and then Metaflow will behind the scenes take care of executing these functions on top of compute resources that are appropriate. So in this example, we have fit model, and I need to execute it on an instance which has 16 CPUs. And again, I can just annotate my function with @resources, and then I'll execute my workflow as I was before. And then Metaflow will take care of creating the appropriate Docker image, publishing the user code, wrapping that up, making sure that all the data is available in that remote instance, executing the user code, then stashing all the data back into the data store, and then going forward. So use cases here could be that, hey, I need to do my data pre-processing, I need to generate my features. And for that, I need an instance that has, say, a terabyte of RAM. So I can have a data pre-processing step, and I can denote that I need, say, a terabyte of RAM for that step. My next step could be a model training step where maybe I don't need a terabyte of RAM, but I do need super expensive GPUs. So for that specific step, I can annotate that, hey, I need a bunch of GPUs for this step. My next step of my workflow could be that, hey, now that I have trained a whole bunch of models, I need to identify which is the best model. And maybe for that step, I don't really need as many compute resources. So I can have a very simple instance for that. And with Metaflow, you can now sort of like very easily specify resource requirements for different segments of your code. And that sort of like then drives up utilization of your compute cluster, which is really, really important for a company like Netflix, where we have so many users running so many different workloads. So efficient packing sort of like becomes really important for us from a cost point of view. Now, another big issue that folks run into is, so up until, so a few years ago, at Netflix, and this still happens to be the case, that every user will sort of like get a VM, which is running a Docker container with a blessed version of all the major machine learning libraries. But then as folks sort of like started working on more and more different projects, the machine learning packages that they needed, they essentially started diverging from the blessed packages that our platform teams were providing. And now that we have complete control over what compute is being executed, we can actually just ask the user what sort of packages and what sort of environment they want. And then we can ship around this sort of like the user function along with the data, as well as along with all the packages that they need around, and we can execute that on their local laptop, we can execute it on the cloud. And the user doesn't have to be sort of at the mercy of what's available via the platform engineering teams as part of the blessed Docker image anymore. And like we have had like use cases where somebody trained a model with TensorFlow 1.14, and now they wanted to migrate to a newer version of TensorFlow. So they just added one more step with the newer version of TensorFlow, so that now they could train 2 models in parallel and then compare and contrast whether it's safe for them to upgrade to a newer version of TensorFlow. So that's one use case. Now, if we look at, say, the kind of life cycle that I spoke about a little while back, right? Once the user has sort of like figured out that this is what my workflow needs to look like, and I have experimented that workflow, and I'm able to scale out my workflow on top of a cloud provider as well, then the next thing is that, okay, Now I need this workflow to execute asynchronously. Maybe this workflow needs to execute every single time I have fresh data available, or maybe this workflow needs to trigger every single time my model performance falls below a certain metric. And what that means at that point in time is that you need to now publish your workflow onto a workflow orchestrator. And many organizations, they have some sort of production workflow scheduler already deployed for their data engineering workflows. And many of these machine learning workflows, if you look at it, they would essentially depend on some of these data engineering workflows. An upstream ETL pipeline might be responsible for publishing data to some specific table. And then as soon as that table partition is generated for the day, for example, then you would want to trigger your model training workflow. But now the gap is that each of these workflow schedulers, they essentially have their own SDKs, their own programming paradigm. And the user, once they're sort of like happy with their local prototyping, then the next thing is that, okay, let me learn the SDK that's being exposed by these workflow orchestrators and rewrite my work so that it fits into the paradigm that's being exposed by the workflow orchestrator. Now, the good thing is that all of these production workflow orchestrators, they also execute a DAG. The DAG might look slightly different, but it's still a graph. And with Metaflow as well, the user has already defined a graph. So theoretically, we can compile down the user graph into a language that these workflow orchestrators understand. And that sort of like allows the user to very seamlessly deploy their prototyping code onto these production workflow orchestrators and sort of like make their work immediately part of the rest of the engineering ecosystem. So for example, Netflix has like a whole bunch of different workflow orchestrators, and these orchestrators, not only do they provide really high uptime guarantees, but then they also very seamlessly integrate into our alerting mechanisms and data auditing mechanisms and so on and so forth. So our users are very easily able to get advantage of all of those capabilities. Now, once you have trained your model and you have, say, a workflow that's refreshing your model at a particular cadence, you still need to integrate that model. A model by itself doesn't really mean much. And there are a variety of different ways of integrating the model. We have internal services, which are tier 1 services, like the Netflix recommendation service, which we can't afford to go down at any given point in time. So numerous engineering teams internally at Netflix have built infrastructure to support model scoring for some of those use cases. And with Metaflow, our users can very simply write a function, and then Metaflow can take care of publishing their model as well as their scoring code into those model serving services. There could be other use cases as well, where for roughly more than half of the use cases of machine learning, they are essentially powering some internal application where the SLA isn't really that high, really that strong. And for that purpose, it's relatively straightforward to sort of like set up a function as a service and then allow our users to very simply deploy snippets of their code on top of that function as a service. So in this particular example, we have this notion of a decorator called @endpoint, where we can simply take the function that the user is specifying. And you can see here in the function that the user has written, the way the model is actually being accessed is through this notion of self.artifacts. These artifacts are essentially available through the flow itself. So if you look at the last line, we have, when we deploy, we pass in the argument training flow /726, which means that we are interested in the 726th execution of training flow. So when we do this deployment, then at that point in time, my model is essentially the model that was trained in the 726th execution of training flow. And that way our users can very simply, every single time there's a new training workflow, new execution of training workflow, they can choose to refresh their hosting endpoints if they need to. So these are like some of the top level functionalities that Metaflow provides. We do have many more features around, like, how do we sort of like deal with high throughput, fast data access. running Spark SQL jobs when 80% of your access pattern is just reading a specific partition of a table can be fairly resource intensive. So we have invested in making sure that we can short circuit some of these query engines and provide our users rapid access to the data that they seek. We have done some work around how can our users better manage their experiments. Collaboration is a big theme for us internally at Netflix, and that sort of like pairs hand in hand with notions of repeatability and reproducibility. So if, let's say, we have a user internally who is working on a project, we want to make sure that their colleagues can jump in and they are able to replicate their work. And by and large, before Metaflow, it was really tricky for users to be able to replicate their dev environment. But now the fact that we are storing pointers to all the data, we have complete knowledge of the environment that they want to execute in, it sort of like makes that story a lot more simpler and straightforward for us. And Metaflow, like in terms of our user base internally, we have a significant number of users who work in R as well. So all the functionality that Metaflow provides, we also support R out of the box. So it's an open source project. And if Metaflow is something that sort of like seems interesting to you, then we also offer cloud sandboxes. So you can just go to metaflow.org/sandbox and you can request a cloud sandbox where we'll essentially provision some compute resources, S3 buckets, and notebook instances for you so that you can try out the cloud scale in real life. And yeah, if any of this was interesting to you, we have a flourishing community on GitHub. Metaflow is being used at Netflix as well as many other organizations, big and large. And yeah, hit me up on Twitter if you have any questions.
Awesome. Thank you, Savin. Great talk. Would you mind stopping the sharing? Thank you so much. Yeah. Yeah, so just a reminder to folks in the audience that you can send in questions in the chat and we'll try to get those to Savin. So yeah, I guess to start us off, I was curious about how Metaflow kind of originated. So I think like one thing I was curious about was I assume, and correct me if I'm wrong, that probably folks at Netflix were doing machine learning and kind of some need arose, right? You talked a little bit about some of the pains that you're solving for data scientists. So I guess one question was just like, what were some of the specific things that you were trying to do where this kind of was the first pass at Metaflow and it helped them? And second, like, did you find that it made it easier down the line to open up new opportunities? You talked a little bit about content creation and kind of how ML is used across Netflix. And I'm curious if this kind of sparked kind of an interest in doing more machine learning across the org because maybe it made it a little bit easier.
Yeah, excellent question. So in terms of the history of Metaflow, if you look at Netflix recommendation systems, like Netflix has invested in those, like, gosh, like I think it's been like more than 15 years. And 15 years ago, machine learning was mostly done in JVM languages, and our recommendations infrastructure stack is still pretty much in the JVM realm. And roughly 4 years ago or so was the time when we started investing in content, in marketing much more aggressively. And there came a need that, okay, like if now Netflix is investing billions of dollars in programmatic marketing, then we need to be great at identifying what ads resonate with our users. And the data scientists in those teams, they were much more proficient with Python and R. And at that point in time, the lifecycle that I walked you through was exactly the lifecycle that we noticed. Our data scientists came to us and they were like, yes, like we want all of this tooling. And the first thing that we did was like, okay, we have a data warehouse, we have a compute platform, we have the workflow orchestrators, maybe you need a model hosting service, we'll go ahead and build that. And we provided and we provisioned all of those toolings. But even then, in spite of that, our users were not really productive enough. And at that point in time, we essentially worked hand in hand with our users, trying to identify what were their pain points, what were those paper cuts. So Metaflow was less of so we didn't go about building Metaflow in the sense that, oh, hey, let's build something and maybe the users will come, but it was more about like, let's now start working with our end users, figure out what their pain points are, try to build something that resolves their local pain points as quickly as possible. And if that leads to building a platform, so be it. If it's sort of like just a cookie-cutter one-time job, we'll go ahead and just do that.
That's awesome.
So that's how we sort of like started. Now, to your next question, yes, indeed, like as you sort of like make people more and more productive, as you sort of like remove bottlenecks, it helps not just in making sure that, the model that was taking them weeks and months to publish to production now takes them hours and days, but it also means that now you're lowering the bar in terms of people who can do machine learning. So one example that I like to give is, like we had an engineer who came up to us and he's like, hey, I have been thinking about building a model where I just want to predict how much time does it take for a video encode job to execute so that I'm not staring at a screen and I can step out and I can essentially go grab a cup of coffee. And it's a very simple, innocuous use case, right? But then if you look at, if you ask like many data scientists, many machine learning engineers, it's still a heavy undertaking because your data is constantly regenerating and you need to make sure that your ML model is also retraining at a particular cadence and all. But with Metaflow, he was able to essentially deploy a model in a matter of days. So we are definitely seeing people introducing machine learning into sort of like the smallest of use cases that would have been prohibitive, a year ago or a couple of years ago. And that was the end goal that we were shooting for, that machine learning isn't sort of like a special snowflake of sorts. And it's not an island. It needs to fit in alongside our existing infrastructure. And how can we sort of like do that without reinventing the world?
Oh, that's fascinating. No, great answer. Thanks.
Hey, Savin, I was wondering, can you talk a little bit about how you guys at Netflix kind of think internally about what makes a good candidate for a machine learning problem? I know at the beginning of the presentation, you kind of gave some examples. One of the ones that really stuck out to me was the idea of using machine learning for the actual content creation, which when I first hear about it, that's not something that in my mind, automatically maps onto an optimization problem. That's, I imagine, creative people doing creative things in a room or something like that. So how do you kind of like think about, like go through that process? Is it, machine learning for content creation? Is that something that you're doing? Any thoughts there?
Yeah, so I definitely want to call out that we don't have machines writing content. So we definitely believe that content creators create the best content, and I don't think machines can sort of like match that level anytime soon. But then if you look at the ecosystem of content creation, there's a lot of manual work that ends up happening, right? Now, if let's say you are shooting a 2-hour-long movie, you need to figure out how to schedule your shots. A movie is not really shot in a linear fashion, so you need to identify when is the cast and the crew available on what dates, and so that you can very optimally figure out that, okay, like let's shoot the climax first and then let's shoot the opening shot on the very last day. There could be also economies of scale that you can leverage if you have multiple productions happening in parallel. And traditionally, how many studios have approached this is there are like huge Excel programs, and somebody spending like days and days trying to figure out what is the optimum shooting schedule. And those are the places where you can just like use optimization techniques and data to inform how to sort of like be much more optimal in terms of using your resources, whether it's money or time or people.
That's very fascinating, Savin. I think that there is a lot of tasks, machine learning tasks, lying around with the company. That's the title of your presentation was the long tail, right? Because there's many tasks that one wouldn't imagine, but they end up being like important tasks for the companies, which is super fascinating.
Yeah, I mean,
I actually have a question that
yeah, go ahead.
Please.
No, so we have use cases internally where like people were like, hey, now that deploying a machine learning model is so simple and straightforward. Can we build a knowledge base on top of all the communication that happens in Slack? So that next time I run into a problem, let's say I'm an engineer and I'm sort of like searching for a solution to an engineering problem, I can definitely reach out to some help channel on Slack. But then a few enterprising data scientists, they essentially took that knowledge base and they created a bot. And you can very simply just ask the bot that, hey, I have this problem. And then it can scan through Slack, figure out if somebody else has asked a similar problem before and point you to that, sort of like a more efficient form of search, more tailored to the Netflix use case. And those sort of instances are the one where, you sort of like get the feeling that, yes, the flywheel of machine learning is in motion and people are now getting more and more creative. And yeah.
Funny enough, a really similar task was tackled when I was at Uber with a model using Ludwig. But, that's the similarities. When you untap the potential for more people to be able to use machine learning, then these things happen, like this little magic happens.
Yeah.
I actually have a question that is a little bit specific and technical about one aspect of Metaflow, which I'm really curious about. When you showed the example with the endpoint, and so the serving story, I would say, you showed, it was like limited to that piece of code, an example where, there were basically two lines of code, one where you were loading the model and one where you were scoring. I'm actually curious about what is a more realistic use case, right? Because I can imagine that, there's a one step where you load the model and a separate step where you actually score. And also within the step where you score, there's also like a pre-processing that needs to mimic what happened at training time and a post-processing that mimic what happened at training time. Can you specify all these things in Metaflow? How does it work?
Yeah, sure. So when you look at model scoring, right, like there's no one single way of scoring a model. And so it can range all the way from, hey, I want to score my model as sort of like part of a batch pipeline. Where, essentially you're writing yet another workflow, or you're just like getting the model somehow and you're putting it in a process and then you're just like churning through all the data that you need to score, to say, I need to set up a dashboard and figure out like the real-time stream of data is coming in and I need to score that and sort of like populate a dashboard. So we have use cases where people deploy these models as Flink apps. The example that I showed you was more in the realm of there's an internal application, say, and it's not really a heavily trafficked application. Maybe, like there are, say, 50 people who are looking at that application on a day-to-day basis during business hours. But then it's core and critical to their workflow. And the QPS is also, say, super low in that scenario. And it would be rather nice if our data scientists are able to automatically deploy, say, a very simple Flask app that is able to score that model. And then our engineers who are actually building that application can directly interact with an HTTP endpoint. And that sort of like also signifies this subtle shift. If you look at, the early 2010s, the way data scientists and engineers would interact was through this notion of a prototype, where the data scientists would prototype, and then you would have ML engineers and other software engineers who would convert that prototype into a production-ready model. And then we sort of like moved into this world where model became the contract, where the data scientists were responsible for publishing a model, and then the engineering teams would consume that model. But so the engineering teams were still responsible for figuring out how to score the model. And now we are sort of like getting into this world where the data scientists, they are responsible for the business logic of like how the model is trained as well as how it's scored. And then infrastructure tooling can essentially take that scoring code and it can embed that in a variety of different contexts, whether it's like batch scoring, real-time scoring through, say, like a Flink app, or say hosting these simple, straightforward microservices, or embedding them into tier one services that are powering the recommendations experience for Netflix. And then that sort of like becomes a much simpler and straightforward operational story at the end of the day. So that's been our experience.
That's great. Thank you so much.
Hey, Savin. I remember reading, as recently as a couple of years ago, that Netflix came under fire for the way that some of the recommendation models exhibited, various forms of racial bias in how they, advertise various shows to various users. I'm curious, did that experience kind of lead to any sort of features built into Metaflow around how ML engineers could maybe better monitor and detect various model behaviors?
So Netflix has definitely, like over the last very many years invested in better machine learning techniques, monitoring techniques. And with Metaflow, essentially what we do is we provide an on-ramp to all of those other internal tools. So the way we sort of like visualize the landscape is that there is excellent work that's happening in terms of building these point solutions, so to speak. So whether it's around like, okay, can we better explain our models? Can we detect bias in our models? Model monitoring, can we train our models at scale? But then moving between all of these solutions is very difficult. And that's where essentially Metaflow comes in, where, so internally we have this phrase called a paved path, where teams are essentially building all of these different solutions. But then as an end user, you essentially want an experience that ties all of these different tools together, so that then the user doesn't really have to interact with all of these individual tools by themselves. So that's been our take. And when it comes to addressing fairness, it's an ongoing problem that, there are many people who are sort of like focused on it. I might not be the right person to address any of those questions around like what our efforts look like at the moment.
Great, thanks.
Hey, Savin, I had a question. So you've done a lot of stuff now to make it easier for people to productionize the models and monitor them. So can you tell us what are the top kind of issues that people run into in production, if there are, like one or two issues that are the most common?
Sure. I guess like now, one of the biggest issue that we are running into is that a single data scientist is able to create many different pipelines. And now how do you sort of like manage the entropy of all the different work that a single data scientist or a team of data scientists is able to do, and provide visibility into those interconnected dependencies? That's the big problem. That sort of like
so some pipelines are failing and it causes downstream issues somehow.
And it causes downstream issues somehow.
Got it.
So how do you sort of like very rapidly identify that who is the offending, what is the offending pipeline? Because some of these pipelines might also be under strict SLAs. So then it becomes rather important for us to sort of like predict what is the blast radius of any failure. So recovering from failure is one aspect, detecting failure is yet another, but then communicating accurately to our stakeholders when failures happen that, okay, this is the amount of time that it'll take for us to recover from any of those failures. That's sort of like a very interesting area of exploration.
Awesome. Yeah, while I have both you and Matej, I wanted to start to get some of the audience questions in. So I'll go through them quickly. But the first one that I think somebody asked was, what is the major difference between Metaflow and MLflow? The two libraries seem to be solving the same ML ops problems, from integrating model training, model serving, and reproducibility. So I figured this would be a good opportunity to maybe get that question answered.
Sure. Matej, do you want to go first?
You can go.
Sure. Yeah. I mean, the way I look at it is there is some overlap, but then there are quite a lot of distinct features as well. And MLflow does an excellent job in not training, but tracking models. And we have many users in the open source community who use Metaflow along with MLflow, where they are able to orchestrate their work through Metaflow. But then within Metaflow, they want to essentially track their model training process through MLflow tracking. And so that's how I essentially look at it, that of course there's some overlap, but then at the end of the day, MLflow and Metaflow, the way they are approaching the problems, they are very complementary. Yeah.
Matej, do you have anything to add there? Or?
No, yeah, I think I agree. And obviously both of these are evolving over time. Yeah, but yeah.
Let me get one or two more questions and then I'll hand it to Dan for the rest. So I think Shreya asked about how data scientists at Netflix are able to train models locally. Since they're probably not going to be able to download data. Can you comment on that? And then just as a follow-on, I think I saw a question about just generally DAG validation. If there's like features built into Metaflow that help people build better DAGs that might be more optimized And I'm curious if there's also features, like personally, I'm curious if there's also features for like what happens when you change the structure of the DAG and kind of make it more fine-grained or more granular.
Sure. Yeah. So for your first question around like, okay, how does local development work in practice? So Netflix has a very data permissive environment. So we don't deal very heavily with user data. So many of our data sets, or like most of our data sets, lack any sort of like PII information, which makes it easy for people to sort of like download some of those data sets into their local workstations. Now, these local workstations are actually cloud-hosted workstations. So the download is not necessarily happening on their laptop. But yes, there's always this instance that, okay, like I just can't store more data on my local workstation. And that's where our scale out functionality sort of like helps, where you have the code, you're writing your code on your local workstation, but now you can very easily just annotate what sort of resources you want for that particular step. And then Metaflow will execute that on a cloud instance. And to the end user, the experience is pretty much the same as if the code was actually executing on their laptop. You can have a scenario where you have a data intensive step, and that data intensive step executes on a remote instance, but then all the subsequent steps, they execute on your workstation. And that's how people are sort of like able to scale out and do their prototyping. Can you remind me what your next question was?
Around DAGs and whether there's any features to help users optimize them, and in general, like how the interaction with DAGs generally works.
Sure. So we definitely link the DAG and make sure that the DAG is valid before executing the user DAG. There's definitely some work that we are doing right now in terms of like figuring out, nudging to the user what are the appropriate resource settings that they might want to use for any of the specific steps, so that they are not overcommitting. There's some work that we have been doing for our container orchestration system that Netflix uses in-house called Titus, around how can we pack more and more jobs and overcommit, because many of the times users specify many more resources than their jobs actually really need. So those are some of the problems that we've been sort of like trying to.
Data scientists are always guilty, and even machine learning people are always guilty of that.
So yeah.
Yeah, I'm glad you brought those up, because we actually had a few questions in the chat about how do you know how many resources you're supposed to ask for. And I think it's really interesting, once you have everything in kind of a centralized system, those kind of systems optimizations that you can make are really, really interesting. I wanted to highlight one question in the chat that I think actually came up a couple of weeks ago when I think Shreya was talking. And that was on, they're wondering, can you share any insights about the impact of the tooling on the bottom line and revenue? Because I think one of the things that our audience members think about is, how do I convince somebody that it's worth investing in tooling and building out these systems in like my own life, in my own companies?
So now the tough part is that revenue attribution for infrastructure tools is a really tough problem. If anybody has figured that out, I would love to know that and calculate, how much Metaflow is responsible for in terms of contributing to Netflix's bottom line. The frank answer is we don't know. But then we have been relying on qualitative feedback from our internal users as well as the open source community. And the fact that people are able to publish more models, get more work done, that's sort of like a mark of success for us. And that's how we sort of like look at like, okay, every passing day, are our end users able to do more with less resources? And as long as the answer is yes, I feel that the team is doing a great job.
Right. I feel like part of that is, tied into questions about how much value ML in general is providing. It sounds like it's being used all over in the company. Can you share any like insights about that? You're probably preaching to the choir, but it's nice to hear those success stories.
Yeah, I mean, I'm just trying to think of something where, there are like any public quantitative numbers available. Nothing sort of like comes to mind that Yeah, I mean, I guess there was a recent blog post on the Netflix tech blog around how the content data science team uses Metaflow to advise our content execs around how should we allocate, like, upwards of $10 billion of content spend every year. So that's a big use case that we have internally, and it's a very involved use case as well. And the health of our business ultimately at the end of the day depends on that, in terms of making better data informed decisions. And all of that work is orchestrated by Metaflow.
Awesome. So we're almost, I think we're at time now. So I think we got through all the audience questions. So really, really happy to have you. Really interesting kind of tooling. I know I've tried to use some of the Conda decorators that you have, and it's been, I think that's one of the features that, at least for my research, I found to be very useful, dependency kind of isolation and so on. So thanks so much for your time. And I want to thank the audience for tuning in. Go to our website, mlsys.stanford.edu, subscribe to our mailing list, and subscribe to the channel. And next week, we're going to have Theodoros Rakatsinas joining us. And until next time, bye.